Hello, today we're starting chapter 9, and although you can see today's lesson is from section 8.7, we're going to talk about something called vectors, which are an important part of chapter 9. So today we're going to look at vectors, but after this, chapter 9 is all about transformations, like translations, rotations, reflections, and dilations. Before we can get into all of those things, we're going to talk about a vector today. You may have heard the term vector from Despicable Me, and if I remember, I'm hoping to attach a little clip for you from that movie. A vector is a quantity or a number in math that describes both magnitude and direction. Magnitude is another term for length, and direction, of course, shows you where a vector points on the coordinate plane. A vector in math looks something like this. Notice that the graph is similar to a ray, where there's an endpoint, a line segment with an arrow, but it's different because there's another endpoint at the tip of the arrow. And that's because a vector does not continue forever, but does have what we call an initial point, where it starts, and an end point, where the vector ends. Vectors are named either by lowercase letters or two capital letters with the vector symbol above, and I'm going to redraw them here because they're hard to see in such a small font. It sort of looks like a ray, except there's only one side of the arrow in the notation, not both sides. Note that when you name a vector, if you're going to name it using 2 points, the initial point must come first in the name, and the terminal point or the end point near the arrow has to go second. We can graph a vector anywhere on the coordinate plane, but the most useful place for a vector is in what's called standard position. Standard position is where the vector is graphed so that it has its initial point at the origin, and then of course the other endpoint can be anywhere on the coordinate plane. So in this next graph, you can see vector CD is graphed here with its initial point C at the origin. When a vector is graphed in standard position, we can write it in what's called component form. Component form sort of looks like coordinates, but it has these pointed brackets instead of the curved parentheses. To find component form, we look for the difference in the x values and the difference in the y values from the coordinates of the initial and terminal points. On our graph here, point C, of course, is at the origin, 0, 0, and point D is located at 4, 2. To write this vector in component form, we'll subtract the x-coordinate from the terminal, the end point, which is 4, minus the x-coordinate from the initial point, 0, and then the same for the y-coordinates, 2 minus 0. Okay, be careful here because the order is definitely important. It has to be terminal point minus initial point. To write this vector in component form, it would look like this. So here's our vector notation for CD equals, and its component form is 4, 2 inside of these pointed brackets. So there are two properties of a vector. One I mentioned is called the magnitude. Magnitude is the length of a vector. So we find the magnitude of a vector using the distance formula. Notice here it shows you that the notation for magnitude looks like this. It has what appear to be absolute value bars outside of the name of the vector. And then the second property of a vector we're going to look at is the direction. And this one is going to be a little more tricky. The direction for a vector is the angle that gets created by the vector and the positive x-axis. And we're going to use some of our skills from the last chapter and our trigonometric ratios to find the direction for different vectors. So let's look at a couple of examples. So in question number 1, it says, graph the vector, write its component form, find the magnitude and direction. So for question number 1, we're looking at vector AB. Let's start by plotting these original points, A and B. So A is here at 2, 7. B is at -3, +3. When we draw our vector, remember that we're going to put the arrow near our terminal point, which in this case is B. So for the first part of this, we're going to find component form. So to do that, we have our vector AB, which is equal to, now we find the difference in the x-coordinates and the difference in the y-coordinates, making sure to use the terminal point first. So for vector AB, that would look like -3 minus 2, comma, 3 minus 7. So in component form, vector AB is -5, -4. Okay, we're then asked to graph the vector in standard form. It doesn't say this directly, but we need that in order to find the direction, so let's just do that now. So now that I have component form, that means that if I were to start my vector at 0, 0, if I move its initial point A to the origin, then the terminal point would now be located at -5, -4. So the same vector in standard position now looks like this. Okay, next we're asked to find the magnitude of the vector. Magnitude is the same concept as length, so we'll use our distance formula. Okay, the notation for magnitude looks like this. The name of our vector inside of what look like absolute value bars. So here for vector AB, to find our magnitude, let's do -3 minus 2 squared and 3 minus 7 squared. So -3 minus 2 is -5, squared is 25. 3 minus 7 is -4, squared is 16. 25 and 16 makes the square root of 41. And let's say to the nearest tenth, that's about 6.4. So the magnitude or length of vector AB is the square root of 41, or about 6.4. The last part of this question is to find the direction of the vector. So I mentioned before that direction is the angle that gets created by your vector and the positive x-axis. Direction is always counterclockwise in math. So if I highlight the positive x-axis here and my vector, the angle that we're looking for is the angle created going counterclockwise by those two things. So here's the angle of our direction. When you consider the coordinate plane, each quadrant contains 90 degrees. So if I measure this angle here, I already know some parts of it. The first quadrant contains 90 degrees. The second quadrant contains 90 degrees. But the rest of the angle beyond that is unknown. And this is where we'll use our trig functions to find the measure of this remaining angle. Our trig functions only work on right triangles, so we're going to use our vector and create a right triangle where the vector is our hypotenuse. We know because of the length and the component form of our vector that this side of our new triangle is now 5 units long, and the left side of our triangle is 4 units long. I'm going to redraw that triangle just so that you can see it a little bit better. So over here, I have my right triangle where the top is 5 units, the left side is 4 units, and the angle that we're looking for I'll call x. If you think of SOHCAHTOA, here we have opposite and adjacent, so we can use the tangent function to create an equation. The tangent of x degrees equals opposite, which is 4, over adjacent, 5. Remember that we're solving for an angle, so ding, 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 we have to use our inverse function. So now x equals tangent inverse of 4/5. And when you type that into your calculator, remember to make sure that you're in degrees. You should get that x is about 38.7. Okay, that number is not our direction. Our direction is the entire angle from the x-axis, positive x-axis, all the way over to our vector. So our direction is actually 90 degrees plus another 90 degrees plus that 38.7 degrees we just found for a total of 218.7 degrees. Okay, if you flip your note sheet over, on the back side, we have a similar example. So let's start the same way. I'm going to graph my original vector with the given coordinates. So this time C is at -3, -2. D is at 4, -7. So our vector looks like this. Don't forget the arrow near the terminal point. Again, we're going to start by finding the component form. So for vector CD, we find the difference of the x coordinates. So 4 minus -3. Difference of the y coordinates, -7 minus -2. So the component form of our vector is 7, comma, -5. We can then use our component form to graph the vector in standard position. So on our graph, standard position has the initial point at the origin at 0, 0, and the terminal point at the coordinates of our component form. So the terminal point will be at 7, -5. So here's vector CD in standard position. Next, let's find the magnitude. Magnitude or length is found using the distance formula. So the magnitude of vector CD is the square root of, for the x coordinates, 4 plus 3 squared, and for the y coordinates, -7 plus 2 squared. So that should be the square root of 49 and 25, or the square root of 74, which is about 8.6. Okay, finally we're going to find the magnitude, the direction of our vector. So here's our positive x-axis. From the positive x-axis, always going counterclockwise. This large angle here is the direction for vector CD. Again, on the coordinate plane, every quadrant is worth 90 degrees. So in the first quadrant, there are 90 degrees. second quadrant 90 degrees, third quadrant 90 degrees, and the last part of our angle that we're missing is this piece here. So we create our right triangle. We always use our vector as the hypotenuse. Because we know the coordinates of our vector, we know that the left side of this triangle should be 5 units long and the bottom should be 7. Again, if I label this little angle here x, we can use our trig functions to solve for that angle. This time we're using tangent again. So our equation would say the tangent of x degrees equals 7 over 5. Because x is an angle, ding, 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 we use our inverse. So x is tangent inverse of 7/5. And when you put that into your calculator, you should find that x is about 54.5. So the direction for this vector is 90 plus 90 plus 90 plus 54.5 for a total of 324.5 degrees. The final part of today's lesson deals with operations with vectors. And again, this will come into play when we talk about transformations later on in chapter 9. We're going to perform just basic vector operations, so addition, subtraction, and scalar multiplication. When you add 2 or more vectors, instead of the answer being called the sum, as it is with kind of typical numbers, when you add vectors, their sum is called the resultant. The resultant is the sum of 2 or more vectors. To add or subtract vectors, you add or subtract, depending on the question, the x coordinates, and then add or subtract the y coordinates. The third operation is scalar multiplication. The term scalar just means a number. So it's multiplying a number, like k, times a vector, where we're essentially using the distributive property. We multiply that scalar number by both the x and the y coordinate of our vector. So in the last couple of questions, we're given 3 different vectors and asked to find each value. So in question number 3, it says, find the resultant, figure out what vector b plus vector c is. So I have vector b, which is -1, -3, plus vector c, 3, 5. To add them, I simply add the x coordinates. So -1 plus 3 is 2. And then add the y coordinates. -3 plus 5 is also 2. In question number 4, we're looking for vector b minus vector c. So -1, -3, minus 3, 5. Again, I perform the operation with the x coordinates first. So -1 minus 3 is -4. And then with the y coordinates, -3 minus 5 is -8. In question number 5, keep in mind the order of operations. Here we need to find 2 times vector b plus vector a. Order of operations says to do our scalar multiplication first. So like the distributive property, we multiply 2 times -1 to give us -2. and 2 times negative 3 to give us negative 6. That then gets added to negative 4, 1 to give us a final answer of negative 6, negative 7. Oops, that should be negative 6, negative 5. Sorry. All right, and question number 6. Again, think about order of operations. We're going to do what's inside of the parentheses first. So if I fill in my two vectors, vector A and vector C, I have 3 times, parentheses, negative 4, 1, minus vector C, which is 3, 5. First, I subtract the two vectors. So negative 4 minus 3 should be negative 7, and 1 minus 5 should be negative 4. And then I perform the multiplication. So 3 times negative 7 makes this negative 21, and 3 times negative 4 should be negative 12. Thanks for listening. Have a great